Hi everyone. In the previous lectures, we started with our discussion on the frequency response of amplifiers. We said that any amplifiers or most of the amplifier circuits can be linearized around a DC operating point, and then that the amplifier can be reduced, the amplifier equations can be reduced to a simple linear differential equations. Now we said once we have linear differential equations, then we use Laplace transforms to solve them because linear differential equations become polynomials in S, and we can use the rich literature of algebraic theory of roots to understand those systems. We spoke about the transfer function, which is the ratio of the input-output transform to the input Laplace transform. Once we know the transfer function, we said we know everything we need to know about a system. We can say if the system is stable or not, and we can also extract the frequency response by just evaluating the transfer function at s equal to j omega. Now, at a later stage, we'll look at how to compute the transfer function. But first, we will say given a transfer function, we discussed how to see if a system is stable or not. We just looked at the poles and we just said if all the poles lie in the left of S plane, then the system is unconditionally stable. The next thing is to draw the frequency response. As an engineer, we should be able to, given a transfer function, we should be able to have an intuitive understanding of how the frequency response will look like. And similarly, if a frequency response graph is given, we should be able to read that frequency response graph as well. And we said one very important point, that to draw this frequency response, where the frequency is going to vary from almost 0 till infinity, and amplitude can also have large variations, we resort to logarithmic functions. Here I have shown the real axis here. So if let x be the real variable of interest, positive real variable, if you take log of x, then all the values between 0 to 1 will be mapped from minus infinity to 0. And all the values from 1 to infinity will be mapped to plus infinity, plus 0, or 0 to plus infinity. So we discussed that it's going to behave like an expanding function in the interval 0 to 1 and as a compressing function in the interval 1 to infinity for x. And we also said for every value a, which is say greater than 1, I can find a corresponding value 1 by a, which is between 0 and 1. And if you take log of a, the log of 1 by a is simply minus of log a. So for every value, positive value from 1 to infinity, I can find a corresponding negative value in the interval 0 to 1. Now let's assume I want to travel all the way till infinity starting from 1. Even though I might jump exponentially a bit, I'm going to jump on points which are going to have exponential variation. So at first I'll go to 10, and then after that 10 square, 10 cube, and so on. Even if I do that, I'll need to take infinite steps to reach infinity. Similarly, if I start from 1 to reach 0, I'll need to take infinite steps. So if I go exponentially, if I start from 10 power minus 1, 10 power minus 2, and so on, I'll need to have infinite steps before I reach 0. So therefore we said it's equally difficult, or rather we said it takes same effort on a logarithmic scale to traverse from 1 to infinity as it is to travel from 1 to 0. And we said this makes intuitive sense because when we discuss amplifiers, we are talking about gains which will have large variations, which will be greater than 1, and also gains less than 1. So therefore we said logarithms make intuitive sense. It makes intuitive sense. Why do we have to go use logarithms? Now in this lecture, what we will be doing is we will try to understand the units decibels and how did the units decibels come about from a historic point of view. And we will also look at how to draw the frequency response given a transfer function. We will take some examples and try to draw the frequency response from a given a transfer function. So to understand how the units decibel came into existence, so I'll again revisit the logarithmic functions again when we start discussing a little bit in more detail about drawing the frequency response graphs. Right now, it suffices to know that the logarithmic function expands the values from 0 to 1 to minus infinity to 0 and from 1 to infinity to 0 to infinity. The point 1 on a real axis before we took the log operation will become the center of this logarithmic universe. So once you take log of x, 1 becomes the center of this new axis, of these new values. So now the log x is going to produce values from minus infinity to plus infinity, centered around 0. And the point 0 corresponds to 1 in the real, in the input variable, which is x equal to 1. Now I'll come back to this. So to first understand how did the units decibel come about, we have to understand the history of telephone communications a little bit, so we'll have a clarity of how did this decibels come into existence. One thing to keep in mind, this was again in late 1800s. Alexander Graham Bell had very famously demonstrated the application of a telephone, so the invention of a telephone. It was later perfected by Edison, especially the microphone part. At that time it was called as the transmitter, the telephone transmitter. But Alexander Graham Bell became an overnight celebrity after displaying his invention, which was a telephone at that time. Now once telephone became a reality, long distance telephony was actually a dream at that time, and they wanted to make it a reality with the invention of an amplifier. Amplifier, vacuum tube amplifier, was invented in the first decade of 1900s. So therefore the understanding of an amplifier was perfected in the next decade, and by then long distance telephonic communications were slowly becoming a possibility. So shown here is this transatlantic cable between the United States and England. And this transatlantic cable is one of the biggest engineering marvels at that time. One thing that engineers had to ensure is that as signal travels along this wire, it induces power loss. So engineers were dealing with, estimating the power loss. Once we know the power loss, then we can insert an amplifier in between, which will amplify and give the power back. So whatever power was lost, it's going to restore it back. So these amplifiers were called repeaters. So engineers were dealing with two quantities. One, they needed a quantity to express loss. So they were seeing losses in the wires. These wires were several miles long. So the losses in the wires. And also they should be able to express the gain that they can provide in these amplifiers, the repeater amplifiers. So they needed a unit to express attenuation, which is the losses, and also amplification. So that's what I've written here. They needed two units, the unit to represent attenuation and amplification. And we said attenuation and amplification can be compared. They are all just ratios of two quantities. In this case, the ratio of powers. Another more easier example that maybe most of you can relate to is an example of a cellular phone. So in today's times, since most of us use cellular technology, the typical power numbers, similarly cellular design engineers are also concerned about the power that a cell tower transmits and the power that a mobile phone transmits and receives. The typical power at a cell phone tower transmits will be in the order of few watts to 10 watts. Now this power before it reaches the cell phone will be significantly attenuated. So for example, I'm going to assume 1 watt. So it will be in fact more than that for a base station, but let's assume 1 watt. By the time it reaches the cell phone, it will be in the order of microwatts or even smaller. So almost the attenuation is the output power, but the input power is almost a factor of 10 power minus 6. So now the cell phone circuits inside the cellular phone, the power has to be amplified back, the signal has to be amplified back. So there will be some amplification happening inside the cellular system as well. So this is why it's important to estimate. If you know what is the losses, then you can amplify, then you can accordingly program your amplification so that you can get the signal back. So that's why we needed a metric to quantify the losses and gains as well. So I gave an example of a cellular system, but engineers were dealing with a similar problems, but they were dealing with wired communications. because there was a physical wire which was carrying the information. In today's times, we have cellular is more popular, so the information is transmitted wirelessly. So the numbers we were dealing with could be of the order of 10 power minus 6 to 10 power minus 10 to 10 power plus 6. You need amplification in the orders of 10 power 6 or 10 power 10. So the losses are mainly here because of the cables. I have shown a picture of cables here. In fact, one of the first transatlantic cables which were laid between the North America and the United States and the United States and the English. It's one of the greatest engineering marvels how it was laid, because they had to carry all the cable on a single ship and lay the wire from one end across the Atlantic. In fact, after many failed attempts, finally they actually carried half of the wires on each of the ships, and both the ships were laying the wires, and at the center, somewhere in the center, the wires were joined together. And telephone communications became a possibility. Of course, there were repeater amplifiers added in between in the wires so that the signal attenuation is tackled. Now we have come to the problem of how to quantify the power loss and power gain. So one of the things we said is that now this power loss and gain can vary all the way from 10 power minus 6 to 10 power 6. Now the variation is significantly larger, so therefore we will directly resort to logarithms. So I'm going to, at that time the engineers were simply taking log of the losses, which will be the output power received divided by the input power, or the power that's being transmitted in the wire at the input. This quantity log to the base 10 was referred to as bells, in the honor of the inventor of telephone, Alexander Graham Bell, and because most of the research at that time was carried out in Bell laboratories. So the name for this unit, which was quantifying the attenuation or the gain that an amplifier should give, as bells. Log of the ratio of the powers to the base 10. So now the thing with this units was that generally when we pick a unit for engineering, especially when engineers pick a unit, we always look at the convenience of the usage of the unit. Preferably, we will always pick units in such a way such that the quantities that an engineer normally encounters should typically be expressed as an integral multiple of that unit. For example, let's say we are dealing with power numbers. So the power in a certain application ranges from say 1 watt to 10 watts. Then we will use watt as the unit, and we will express power in multiples of a watt. So 1, 2, 3 or 10. But now if the power numbers that we are dealing with happens to be in the range of say 0.001 watt or less, or probably it lies between 0.0001 to 0.01. In that case, using watts really doesn't appeal, or rather we would prefer to have an integral multiple of the fundamental unit, or the fundamental unit that we are going to use here. In that case, it's easier to use milliwatts as a unit, so that the numbers look more as an integers. So then if you use milliwatt as a unit, 0.01 becomes 0.1 watts, 0.1 milliwatts, and 0.001 will become 1 milliwatt, and 0.01 will become 10 milliwatts. So in the same way, when we are describing power using bells, if let's say we want to this quantity log to the base 10 of P out by Pn, let's say the power is varying from 10 power minus 5 to 10 power plus 5. This is a really large variation. If I feed it to this function, I'm going to get the outputs which are varying from minus 5 to plus 5. So the outputs will be between minus 5 bells to plus 5 bells. Now this is a very coarse representation. I mean, the range is really much larger, but I'm compressing or reducing it to a smaller range. It looks like I'm looking at minus 5 to plus 5 is really a very small range. So for the same reason why we adopted a different unit, I mean the units are the same but a different version of the unit, it's mainly because of more of a user friendliness of the quantities of interest. So therefore, instead of expressing it in bells, if I express it in decibels, so here milliwatt is 1,000th of a watt. Okay, so I can express it in decibels. Decibels will be 1/10 of a bell. So now I'm going to multiply and divide by 10. So I'll write it as 10 log of P out by P in into B by 10. Now if you see, this term B by 10 is what we refer to as dB or decibels. Now B here should be a capital letter because it's the name of a scientist, and D here is in small letter. So it's deci, 1/10 of a bell. So this unit here, 10 log of P out by Pn, is the unit for the power loss or gain in decibels. So that's how the unit decibel comes into existence. Okay, so if, for example, if the power numbers or the power loss numbers happen to be even smaller in numbers, okay, it's much smaller. So for example, if you see, if your output power to input power ratio is 10 power 0.1, then we can say they differ with each other by 1 decibels. Now if you are dealing with numbers smaller than 10 power 0.1, then maybe we can express them in a different unit, decibel to centibels. 1 centibel is 1/100th of a bell. So you will see larger units that we are dealing with. Okay, so 1 centibel will be 1/10 of a decibel. So whatever units we got from decibels, you just have to multiply it by 10 to get the centibel units. So C is again small here, B is a capital letter. But most of the times we stick to decibels. For most applications, decibels suffices. Now the same definition, so this was the definition which was introduced for powers. We can apply the same definition to voltages too. So we discussed this even in the previous lecture. We said power is generally proportional to voltage square. The input power and output power are proportional to input and output voltage squares, the squares of the input and output voltages. Using that, here I am assuming the resistor across which the power is being dissipated is the same, but it's just a convention. We can replace P out by P in with V out square by V in square. So then we will get 20 log of V out square by V in, V out by V in. So if the ratio is for voltages, we take 20 log. That follows from this. We start with 10 log for power and substitute power as voltage square. We get 20 log for voltage quantities. So the most important thing here to understand is decibel is always a ratio quantity. It's a relative quantity. It's the ratio of two quantities. But now the idea of decibels is often expressed in a wide range of fields in electronics. For example, let's say a power electronics engineer is dealing with voltages which have large variations. So it can vary from say 0.1 volts to all the way say hundreds of volts. So here again the voltage range is pretty large. Even here we use some clever definitions using decibels. So always remember, decibel is a ratio of two quantities. So here again we define a reference with which we are going to compute, with respect to which we are going to express every other voltages as a decibel format. So what we'll do is we'll take 20 log, let the voltage of interest be Vx divided by 1 volt. I'm going to compare all these voltages to 1 volt and express them in decibels. So whenever there is a large variation, I said engineers prefer to use decibels, logarithmic functions, which in this case happens to be decibel units. So 20 log of Vx by 1 volt. So for 0.1 reduces to, so it will be 20 log of 0.1, which will be minus 20 decibels, dB V. So generally when we write decibels, it's a ratio of two quantities. But in such cases wherein we are trying to express a voltage itself in terms of decibels, we have to write dBV. This is just to say decibels with respect to a volt. Okay, so when you write dB, it's usually a ratio of two quantities. Even here it's a ratio of two quantities, but since we have written dBV, now that is enough in information to tell what voltage does this correspond to. If you look at this ratio here, if dB units are given to you directly, if units are given to you directly in decibels, you can't really say what is the absolute value of P out or what is the absolute value of P in. So that we cannot say that from the knowledge of dB. It just tells you how much loss the power has endured or how much gain it has experienced. But in these units, where I've written dBV specifically, you will know clearly what is the voltage levels. Because dBV is defined with respect to 1 volt, you can say clearly by looking at minus 20, you can say the voltage is 0.1 volts. Similarly, 20 log 100 is going to be 40 decibels. 40 dBV, sorry. So decibel with respect to volt. So in the same way, we can define for currents as well. Since power is again proportional to current square, so we can express the ratio of output current by input current and in decibels as well. So that will be 20 log of I out by IN. We can start with this definition, 10 log of P out by P in, and assume that the power is being dissipated across the same resistor. So then you will get I out square R, P in will be equal to I in square R. You take the two ratios, you will end up getting 20 log of I out by IN decibels. In the same manner, if I'm dealing with a system which has large variations in currents, which has huge variations in currents, say ranging from few of 0.1 amperes to several hundreds of amperes, then we can employ in a similar way a unit called dBA, decibels with respect to an ampere. So there we are going to consider a current Ix is the current of interest, normalize it to 1 ampere, divide it with 1 by 1 ampere and take log of that quantity, because logarithms we take them always for ratio of two quantities. In some very specific applications like oscillators and some noise circuits, we do take for direct voltages and some radian quantities, but right now I'm not going there. I'm just sticking to the simplest examples where logarithms are used, the decibel units are used. Similarly, if you are dealing with smaller currents and smaller voltages, we can define dBmV, decibels with respect to a millivolt. So where I can define 20 log of Vx upon 1 millivolt. So the reference unit is 1 millivolt. So then I should write it as dBmV. A more popular way of expressing power in cellular system also uses a similar definition of this dB. So for example, if the powers we are dealing with is in the order of 1 watts to 10 watts, in the same way as we define dBV, we define dBW, decibels with respect to watt. So we take 10 log here, so for power, so we take 10, Px being the power of interest divided by 1 watt. So if you know, for example, if I give you plus 30 dBW is the power, we can exactly say what is it in watts. So it's going to be 10 power 3 watts. So we directly know if we look at a dBW number, we already know the power itself. But in a dB number, we can't exactly say what's the output power or the input. We cannot say that. It's just a ratio is something that we are aware of, but the exact values are not obvious from the dB value. Similarly, we can use the same definition for power for smaller numbers in power, which is more popular in cellular systems, called dBm. So we take, instead of 10 log power normalized to 1 watt, we normalize it with 1 milliwatt. So we are comparing with 1 milliwatt and express this unit as dBm. So dBm is for power, and similarly if I want to compare it with 1 microwatt, then I'll use dB mu. So this is power expressed and compared with respect to microwatts. Again, the units can be chosen based on the range of powers the engineers are operating on. So for example, a 1 milliwatt power in dBm will be plus 0 or 0 dBm. A minus 30 dBm power will correspond to 1,000th of a milliwatt. So it will be 10 power minus 6 watts or 10 power minus 3 milliwatts. Similarly, a plus 3 dBm, plus 30 dBm will correspond to 10 power 3 milliwatts or a watt of power. So this is how decibels The units were introduced around 1920s, the idea of decibels and all of that, which was slowly getting accepted in the engineering community. And eventually, it's been nearly a century now. So these are other common popular places where we use the decibel units. And what I've discussed is a range of modified decibel units which are used for different applications. So we have seen dBm, dBmu, these are the numbers which are used in cellular applications. And we've also seen dBV and dBA. These are the numbers which are used in power amplifier, where we will be dealing with really large ranges of voltages and currents. So that's it about the discussion of the decibels and the motivation why how did the units decibels come into existence. Now we'll quickly talk about frequency response of amplifiers, how to plot the frequency response. We said once we know the Laplace transform h of s, all we need to do is evaluate h of s at s equal to j omega and we get the frequency response. Now since frequency response is a complex number, it has both magnitude and phase. The magnitude we plot 20 log of, so again we will mostly be dealing with amplifiers where voltages are input and voltages are outputs. So h of omega, the units will typically be volts per volts. So therefore, we should take 20 log of mod of h of omega. Now this is the frequency response of this amplifier. Now if I want to plot this frequency response, I'll take some simple examples. If I want to plot a complex frequency response, it's better to understand how to plot it for simpler transfer functions, and then for a more complex system, using the knowledge from simple transfer functions, we should be able to draw a complex transfer function or a complex frequency response. So first I'll start with the simplest transfer function, which is h of s equals 1 by s. Now this system has no zeros. If I want to find zeros, I'll have to equate it to 0. Then the 0 is at infinity. So there is no real finite 0. The 0 is at infinity. But this system has a pole at s equal to 0. So now I'll evaluate. So when we have a pole at s equal to 0, we can say the system is marginally stable. It's not, for some inputs the system can become unstable. So that's why we use the word marginally stable. For some specific inputs, the systems can generate unbounded outputs. For example, if I feed a step input to the system with the transfer function 1 by s, so very quickly to discuss what is 1 by s, if you take an impulse response delta of t, the Laplace transform of impulse response is 1. So if you integrate Laplace transform the impulse once, you get 1 by s as your Laplace transform of a step function. So the impulse response of a system with transfer function 1 by s is u of t. So if you actually convolve x of t convolve with u of t, you can readily show that this is an integrator. The output y of t will be given by integral minus infinity to t x of tau d tau. This system with a pole at dc s equal to 0 is an integrator. Okay, so if I, for example, if the impulse response was delta of t, it's an identity system. You pass x of t, it's going to come out as it is. If you pass through a derivative of an impulse del dash of t, if you pass x of t, you will get x dot of t, it's derivative of x of t. If you pass it through an integral of delta of t, that's u of t, and if you feed x of t to that, your y of t will be integral of x of t. So this is one way of quickly looking at what's happening when I pass it through a system with an impulse response of u of t, because u of t, the step function, is an integral of an impulse function. So if you take an impulse and integrate it, so you have an impulse, you integrate an impulse function, so it will be 0 all the way here. After this point, the impulse usually integrates out to a finite value, even if you integrate it for no time. So you have a sudden step change in voltage here, and that step will remain constant forever. Okay, and the step then will remain constant forever. So this step function u of t happens to be an Yeah. So this step function here, u of t being the step function, it can be written as integral of an impulse function. So therefore, if I feed a function x of t, the output will also be an integral. The output will be an integral of the input function. So now, if I feed a step input to the system, the output is going to be integral of step. The integral of step is a ramp function. Sure, it's a unit ramp. And in the steady state, even though the input is bounded here, in the steady state, this output is going to go to infinity. So therefore, for this specific input, the system is actually producing an infinite output. So therefore, this system is unstable. A more general definition for stability of a system, it's called absolute integrability. You take the impulse response of a system. If you have a system with an impulse response h of t, again, if you take the Laplace transform of h of t, you get the transfer function h of s. Take mod of h of t and integrate it for all time. If that value converges to a finite value, which is less than infinity, means it's a finite value, then we can say the system is stable, unconditionally stable. This doesn't hold true for a step function. If you integrate u of t for all t, you will get infinity. So it's an unstable system. So now we'll try to plot the frequency response of this system 1 by s. We just discussed very briefly what the system is. I'm going to now draw the frequency response of this system. To draw that, I'll substitute s equal to j omega. Now this is a complex number with minus j by omega as the transfer function. Right now in this lecture, I'll mainly focus on drawing only the magnitude response. We'll talk more about the phase response in the upcoming lectures. So if I take mod of this, I'm going to get 1 by omega. So now I'll take 20 log. I'm going to take 20 log of 1 by omega and try and plot this function. Now this function, if on a logarithmic scale, if you look at it, what we are going to do here is that we are going to plot this function as a function of frequency omega. Now you have to keep in mind, I said it's a log-log graph. Frequency is also on a logarithmic axis. So what I'm plotting here is log of omega. And this function here, 20 log of omega, can also be written as minus of 20 log of omega. So the transfer function mod of h of j omega, I have taken 20 log of this quantity, which is what I'm trying to plot. This is my y-axis. And the x-axis is log of omega. So this looks like a linear equation. So if I take log of the output, which is 20 log of this quantity, and this log of with respect to log of omega, it looks like a linear quantity with a slope of minus 20. Okay, it looks like a linear expression with a slope of minus 20. So now, but since I have taken log of omega, to express the slope properly, I'll now draw this line. It's going to look like a linear line. So since the slope is negative, it's going to be like this. At omega equal to 0, when omega is 0, log of 0 will be minus infinity, so you will get plus infinity. This function will become plus infinity, which I have not shown in the graph. And at omega equal to 1, it will go to, so I'll draw it differently. At omega equal to 1, it will reach 0 decibel line. It will cross the 0 decibel line when omega equals 1. Now the question is, what is the range of frequencies should we be showing this graph for? So remember, we said it's a log-log graph. Your frequency is going to vary from 0 till infinity. So we can't show all the frequencies in the same graph, in one physical graph. So in fact, let's assume this frequency where it is intersecting, instead of 1, let's assume it is some frequency omega naught. To reach 0, it's a logarithmic graph, so I'll hop exponentially, meaning I'll hop decade by decade. So since I'm taking log of base 10, if I want to reach, let's say I'll go for infinity first. If I want to reach infinity, I'll hop from omega naught to 10 omega naught, then to 10 square omega naught, and so on. So I'll need to hop infinite such decade. So this is one decade of a frequency. Omega naught to 10 omega naught is one decade of a frequency. If I want to hop decade by decade, I need to hop infinite such decades to reach infinity. In the same way, to reach 0, I'll again have to hop infinite such decades. So I have to go from omega naught to omega naught by 10, then omega naught by 10 to omega naught by 10 square, and so on till omega naught by 10 power infinity. So I need to hop infinite times, so therefore I can't really show 0 also on a log graph. In any practical graph, I won't be able to show 0. So I'll just show this as an asymptotic line reaching minus infinity. It's a straight line equation and it will reach minus infinity. The important things to look for is where does it intersect this 1 dB line, as the 0 dB line, and that happens to be when omega equals to 1 radians per second. The units here is radians per second. Now the next thing to note is what is the slope with which it is increasing or decreasing. Now let's say I move 10 times from 1. I'm moving away 10 times from 1. So let me just call this frequency here. For this example, it is 1. I can consider a transfer function that looks something like this. H of s, instead of 1 by s, I can consider a transfer function omega naught by s. In that case, I'll also get a function omega naught here. So this value, instead of minus of 20 log omega, it's going to be 20 log of omega by omega naught. Minus 20 log of omega by omega naught. The value of this function at omega naught, this value will be 0 dB. Minus of 20 log of 1 to base 10, it will be 0 dB. Now I'm going to increase omega to 10 omega naught. So I've increased by 1 decade. If I increase by 1 decade, the value of this is going to be minus 20 decibels. So if I change my frequency by 1 decade, the output will reduce by 20 decibels. So the slope here is minus 20 decibels per decade. And the slope follows through. It's a single straight line equation, so it will have a single slope. The slope is given by minus 20 decibels per decade. So this decade here refers to 1 decade in the change in frequency. The slope here is minus 20 decibels per decade. So for example, let's assume at some frequency omega naught, or since we know the value of this function at omega naught is 0 decibels, the value of this function at omega naught by 10 is going to be, because I am now reducing the frequency, so the amplitude should increase, it's going to be plus 20 decibels. So with the knowledge of the slope and location of omega naught, I can predict any value by using this relationship. So you know the slope is, for us, if you have one pole, the slope is going to be minus 20 decibels per decade. I will talk about the phase response a little later. Now let's consider two poles, which is 1 by s square. So let me take omega naught square by s square. So I have considered a transfer function which looks like this. So here again the system has no zeros. It has two poles at s equal to 0. It has two poles at s equal to 0. Now if I take the magnitude of the substitute s equal to j omega, we get minus 1 by omega square. You take the magnitude of that, you get 20 log of 1 omega naught square by, this is omega naught square by omega square. You get omega naught square by omega square. This function then becomes minus of 40 log of omega by omega naught. In the same way, if I want to draw this graph, the value at omega equal to 0, again it is plus infinity, because log of 0 is minus infinity, multiplied by minus 40, you get plus. I can't show this in this axis. 0 frequency cannot be shown in the axis. So we'll start with some frequency omega naught. At omega equal to omega naught, it is 0 decibels. As you increase omega naught by 1 decade, so if I increase omega naught by 1 decade, so if I want to find its value at 10 omega naught, here now we have two poles. The slope is going to be, the value is going to change by minus 40 decibels. At omega equal to omega naught, it was 0 decibels. At omega equal to 10 omega naught, the value of this function is minus 40 decibels. So it has changed by minus 40 decibels in 1 decade. For a decade change in frequency, the magnitude reduced by 40 decibels. So the slope will be minus 40 decibel per decade. So this slope here is minus 40 decibels per decade. And the function is going to look something like this. The slope here is minus 40 decibels per decade. Just for the sake of comparison, for a single pole system, if I had just omega naught by s, the transfer function had a different slope. It had slightly smaller slope. It intersected at the same point at omega equal to omega naught. It was also 0 decibels. But the slope here was minus 20 dB per decade. Here the slope is minus 40 decibels per decade. Now if I consider a transfer function of this type, omega naught by s whole power n, so wherein we have n poles at s equal to 0. N poles at s equal to 0. In that case, you can directly see that here, if you substitute, so you will get the transfer function as 20 log of omega naught divided by omega, the whole power n. So it will be whole power n. I can write it as minus of 20 log of omega by omega naught, 20n log of minus of 20n log of omega by omega naught. So you can see here the slope is minus 20n. So if you keep adding more and more poles, the slope will keep on increasing and it will go to minus 20n decibels per decade. Similarly, if you consider a 0, I'm going to directly consider an nth order 0. So you have a transfer function like this of this type, s by omega naught whole power n. So here we have n zeros at s equal to 0. So if I try to solve this equation, I'm saying it's s power n. So there are n zeros, same zeros at s equal to 0. So in that case, if I substitute s equal to j omega and take mod of it, I'm directly going to get something of this type. So I'm going to get 20 log of omega by omega naught whole power n. So we get 20n log of omega by omega naught. Now if you look at this function, on the other hand, it's increasing as a function of frequency. So you can see here, this function 20n log of omega by omega naught, if I increase omega, this function is going to increase. Logarithmic function is an increasing function. It's going to increase. At omega equal to omega naught, it will be 0 decibels. You get 20n log of 1, which will be 0. Now if I increase omega naught to 10 times omega naught, if I increase the frequency to 10 times omega naught, you can see the output will be plus 20n decibels. So in 1 decade, if I just increase by frequency by 1 decade, the change in the amplitude is 20n decibels. So the slope here will be plus 20n decibels per decade. Now remember, this equation has s equal to 0 as a 0. So therefore, if I evaluate the transfer function at DC at omega equal to 0, it's going to approach minus infinity. So that's what I've shown here. Again, I'll show this asymptotically. It's never going to touch on a real, in any practical finite graph, you can't show omega equal to 0 and omega equal to infinity. So we'll just show this as though it's just reaching minus omega equal to 0. So if I traverse to a frequency of value omega naught by 10, which is omega naught by 10 radians per second, we can easily say the value here is going to be minus of 20n decibels. For a system of this type, omega naught by omega the whole power n, omega by omega naught the whole power n, omega by omega naught the whole power n of this type, we can say the slope will increase with a slope of plus 20 decibels per decade. So if I decrease by 1 decade, the amplitude will also decrease by minus 20 dB. Now we'll consider some practical transfer functions, real poles with non-zero poles and zeros, real systems with non-zero poles and zeros. Shown here is a simple first order system with one pole. If you equate the denominator to 0, you get the pole which will be at minus omega p. and the DC gain, which is the gain at omega equal to 0, happens to be A0. So this is the DC gain or the low frequency gain of the system. So to plot this function, what we will do, to find the frequency response, I'll substitute S equal to j omega. So I'll get A0 by 1 plus j omega by omega p. To plot this function, I'm going to approximate this function for small values of omega and large values of omega. I'm going to consider two cases when omega is much smaller than omega p and when omega is much greater than omega p. So first, it's a complex number, so I'll take its magnitude. So I'm going to get A0 upon root of 1 plus omega by omega p the whole square. Now this function again, I'm going to plot this as a function of frequency. So I've taken 20 log on both the sides. So this is 20 log of your transfer function, and now we are supposed to plot this function as a function of frequency omega. Now I'll use this condition. First I'm going to assume omega much less than omega p. Because it's a single pole system, we will see the behavior of the system around omega p. So for omega much smaller than omega p, this function here, I can ignore this value since omega by omega p is going to be much smaller than 1. If you satisfy this condition, I'm going to get the gain approximately equal to 20 log of mod A0. So that's what I've written here. So this will be your gain function. So I'll write it as a straight, I'll draw a straight line this way. So that's how your amplifier is going to behave for lower frequencies. When I say lower frequencies, for frequencies where omega is much smaller than omega p. The next condition is what happens when omega is much greater than omega p. If omega is much greater than omega p, this relationship, so 1 plus omega by omega p the whole square will be approximately omega p by omega p itself, whole square itself. So you take the root, you are going to get 20 log of A0 divided by omega p. So this expression, I can further reduce it and write it as 20 log of A0 minus 20 log of omega by omega p. I can write it as this way. Now if you look at this equation, I am plotting the transfer function, which is 20 log of mod of h of j omega or omega with respect to this log of omega. If you see here, I get a linear equation in log of omega. So for frequencies much greater than omega or omega p, the function is going to look like a straight line equation. So this is omega p. I'm considering frequency which is much greater than omega p. It's going to look like a straight line equation. Now if I equate the low frequency value, which is 20 log A0 equals to, so if I equate these two, so 20 log mod of A0 equal to this, the point where they both intersect is at omega equal to omega p. So that's where they both intersect. So this graph, when you now complete the graph, low frequency to this point, and you join the high frequency lines and the low frequency lines, it's called the bode plot. Now you should understand how does it compare. We have made approximations to draw this graph. So this is something that's very useful for hand analysis by engineers. We should be able to draw it by hand. So that's why we made approximations to draw them. But how does it compare to the actual function itself? To see that, we'll first try to calculate the value at DC. At omega equal to 0, if you calculate the value of this function, you're going to get 20 log A0. So both the values are going to match exactly at the values at omega equal to 0. Similarly, at omega equal to infinity, this value is going to become 20 log of 1 by infinity, which will be minus 0, which will be minus infinity. And that is also predicted, and that is also predicted by this equation. If you substitute omega equal to infinity, you should get minus infinity as your answer. So we are fine at both the ends. So I'm going to show here at both the ends here. I'm going to show in pink the actual curve. So I can't show infinity on this graph, but let's assume this tip somewhere at the end is infinity. Only at these 2 points the graph matches with this. Because if you look at this function, at any value of omega greater than omega p, at any value, the denominator will be greater than 1. Therefore, the numerator will be less than a0. It will be a0 by a number greater than 1, so it will be less than a0. So therefore, the graph will look something like this. The actual graph will, again it will be less here as well, because we made approximation, it's going to be less than that. It's going to be less here as well. And both these graphs, the actual graph which I'm going to show in pink now, will touch the bode plot as it's asymptotically. The actual plot that we drew, the plot in yellow, it touches it asymptotically. It's going to touch it at 0 and infinity, but nowhere else it's going to touch it. It's not going to match anywhere else. So therefore we call it as an asymptotic plot. The plot shown in yellow, it's an asymptotic plot. It matches the actual plot only asymptotically. Only at the extreme conditions, the boundary conditions at 0 to infinity, they exactly match. Otherwise there will always be some small error. So the actual graph, here if you see, we have drawn the graph intersecting at omega equal to omega p. The value here looks like it is 20 log a0, mod a0. But in an actual bode plot, in an actual frequency response plot, if you calculate the value at omega equal to omega p, you will get this value to be, if you calculate it at omega equal to omega p, this value will be 20 log of a0 upon root 2. So which is 20 log a0 minus 20 log root 2, which will be 20 log a0 minus 3 decibels. The gain actually reduces by 3 decibels at this point. So this value difference will be 3 decibels. So this frequency where this gain for a single pole system is called the 3 dB frequency or half power frequency. It's also called half power. We'll discuss half power later. It's the point where the gain reduces by 3 dB. In a single pole system, it's called the 3 dB frequency, or also the 3 decibel bandwidth. It's the frequency where the gain reduces to 3 decibels of its low frequency value. So the conclusion here is that bode plot is what I've shown in yellow. It's an asymptotic plot. But it does help us significantly in understanding how the frequency response of the graph will look like, because it more or less matches the graph pretty closely. And we need to know a few points. The point where there is a pole, it will be off by 3 decibels. So this knowledge is already present with us. So now I'll try to slightly make the transfer function more complex. So now what if I have two poles? So now I have added 2 poles at s equal to omega p. So substitute s equal to j omega here and take its magnitude. So you will actually get a0 upon 1 plus omega by omega p the whole square. So now if I express it in decibels, you will get 20 log a0 minus, I am going to talk about frequencies much greater than omega p. For frequencies much less than omega p, this is going to be just 20 log a0 itself. So that I can show it as a straight line here. For frequencies less than omega p, it's going to look like a straight line. For frequencies much greater than omega p, I can ignore 1. I can write this as minus 20 log of omega by omega p the whole square, or I can write it as minus 40 log of omega by omega p. So this looks like a linear equation in log of omega. So therefore I can actually plot this function as a straight line. This will be a straight line, and the slope of this straight line will be minus 40 decibels per decade. So you can very easily verify that here. If I assume frequency, let's assume I'm changing my frequency by 10 times. If I change my frequency omega by 10 times, then it's going to change at the rate of 40 decibels for every decade change in the frequency. So that we have already seen how it does for a polar DC system. So the same thing holds true here as well. So if I change my omega by 10 times, then the gain will, if I increase my omega by 10 times, the gain will reduce by 40 decibels. So for a decade change in frequency, the gain reduction is minus 40 decibels per decade. So the graph, you just have to join both these lines, and this point where it intersects will be omega equal to omega p. Now at omega equal to omega p, since there are two poles, the gain would have reduced by 20 log of 1 by 2, so which is 6 decibels. So it will be 20 log of A0 minus 6 decibels. So 20 log of 2 is 6, so it would have reduced by 6 decibels. Now I can generalize this and assume n poles. If I have n poles, 20 log n, the graph will look the same. It will look the same at low frequencies. The DC value is the same, because when I substitute s equal to 0 or omega equal to 0, the DC gain is still A0. So low frequency part will look the same. But for frequencies much greater than omega p, this function, it's going to decay down with a much faster slope. So it's going to look something like this. So if I try to show on the same graph, if I show this is the first order system, the slope of a first order system is minus 20 decibel per decade. I did not mention this in the previous example when we were talking about the Bode plots. This slope here is minus 20 decibels per decade. So since we analyzed the slopes for an integrator with one pole at DC, I thought it's pretty obvious, but just for the sake of clarity, the slope here is minus 20 decibels per decade. So you increase the frequency by 10 decibel, 1 decade, the gain will reduce by 20 decibels. So now if I take a second order system, the plot is going to look something like this. So this slope is minus 20, this slope will be minus 40 decibels per decade. If I take an nth order system, which means I have n poles at DC, n poles at omega p, it's going to fall off with a slope of minus 20 n dB per decade. It's going to fall off much faster. The interesting thing is, what is the value at omega equal to omega p? At the value at omega equal to omega p, if you looked at it the way in which we were writing this equation, if I evaluate this at omega equal to omega p, I'll get 20 log of A0 minus 20 log of omega by omega p power n. So this will be, you should actually apply this j omega and find its magnitude. Since there are n poles, for example, if I take 1 plus s by omega p, the magnitude of this at s equal to omega p is A0 by root 2. Since we have n such poles, it will be root 2 power n. So we should subtract minus 20 log of root 2 the whole power n. So you will get minus 20n log of root 2. So log of root 2 is 20 into log of root 2 is 3. So you will get minus 3n decibels. So if I have a n pole system at m pole system with all the poles at omega equal to omega p, at omega equal to omega p, the actual Bode plot will be minus 3n decibel times lower than what it is on a Bode plot graph. The actual frequency response graph will be 3n decibels lower. The next function which we are going to draw for is a zero. A system with a DC gain of A0 here, and this system has a 0 at, so equate the transfer function to 0, you get 0 at s equal to minus omega z. Now to plot this function, again I use the same condition, omega much smaller than omega z and omega much greater than omega z. The transfer function is going to be root of 1 plus omega by omega z the whole square, 20 log of this. For lower frequencies it will be 20 log of A0 itself, so that's what I've drawn here. And for much higher frequencies it's going to be, I can ignore 1 here, it will be 20 log of omega by omega z. So this is a straight line equation with a slope of, see, it's plus 20 log of omega by omega z. So the slope will be, for every 1 decade in increase in frequency, the gain will increase by plus 20 decibels. So I can say the slope is plus 20 decibels per decade if I look at this function. So after omega equal to omega z, you are going to get this graph, and if you draw both these graphs, they will intersect at omega equal to omega z. In an actual graph, if you calculate the value at omega equal to omega z, you get 20 log of plus root 2, which is plus 3 dB. So the actual graph is going to look like this. Again, it will touch only asymptotically, so that's why Bode plot is an asymptotic plot. This is the yellow graph which touches the actual graph asymptotically at 0 and infinity. And at the point of the pole, or in fact in this case 0, it's plus 3 dB higher than the DC gain. So it is plus 3 decibels here. In the same way, I can extend this to n first order system, n zeros at the same point at s equal to minus omega z. If I do that, if I consider a system of this type, a naught into 1 plus s by omega z the whole power n, then we can clearly show that I'll draw it on the same graph. The DC gain will remain the same, but the high frequency transfer function will look different. At very high frequencies, you will have 20n log of omega by omega z. So the slope will be much larger. So it will increase at a much larger slope as shown here. So the slope will be plus 20n decibels per decade. So you change the frequency by 1 decade, the amplitude will increase by 20n decibels. When you draw the actual Bode plot, you will see that at omega equal to omega z, you will be off by, again this you can very easily show the same way we showed it for a pole, it will be plus 3n decibels higher. In case of a pole, it will be 3n decibels lower. In case of a 0, it will be plus 3n decibels higher. So now we saw how to draw a transfer function for poles and zeros. Some important takeaway points here is that the transfer function, if I have a pole, it will remain flat. If I just have a pole, it will remain flat for lower frequencies. After you encounter the pole, it will roll off. It will start decreasing with a slope of minus 20 decibels per decade. If I have higher order poles, more and more poles at the same point, it will start decreasing with a slope of minus 20n decibels per decade. So if it's a 2-pole system, it will be minus 40, 3-pole minus 60 decibels per decade, and so on. Similarly, if I have a 0, the Bode plot will look something like this. At low frequencies, it will be constant. After it encounters 0, the gain will start increasing. It will increase with a slope of plus 20 decibels per decade for a single 0. If I have nth order 0, it will increase with a slope of plus 20n decibels per decade. Now with this knowledge, we will try to draw transfer functions given, we will try to draw the frequency response given the transfer functions. So given here is a transfer function that's showing 1 plus s by omega 1, and it is given omega 1 is 1 megahertz and omega 2 is, so omega 2 here is 100 megahertz. So now we are supposed to plot this transfer function. To plot the transfer function, first I'll have to start with the DC gain. DC gain, find omega equal to 0. You get, at omega equal to 0, you get 1 by 1. So you get 0 decibels. So the DC gain is 0 decibels. Now first you have to look at this function. This system has 1 0 at omega 1 and a pole at omega 2. Now 0 is at a lower frequency. It is at 1 megahertz. So first you will encounter 0. So the moment you encounter 0, the gain will now start increasing with a slope of plus 20 decibels per decade, because it is 1 0 plus 20 decibels per decade. Now this increase will keep on continuing till 100 megahertz. That's where you encounter a pole. Now we know the moment you encounter a pole, your transfer function will start decreasing at the rate of minus 20 decibels per decade. So now the function is trying to decrease at the rate of minus 20 decibels per decade, but because of this 0, it is trying to increase at the slope of plus 20 decibels per decade. So after you encounter the second pole, the effect of pole and 0 will cancel out and the transfer function will remain constant. It is the sum of these two responses, it will remain constant. So we should take 20 log, it's the response of this plus the response of this, it will remain constant. So this is how the transfer function looks like, and roughly if you are to estimate what is this steady state, what is this peak value, that we can estimate from the knowledge of what we have so far on bode plots. We know the gain here is 0 decibels at lower frequencies. So close to 1 megahertz, if from this equation, straight line equation, I can directly say at 100 megahertz you are increasing the frequency by 2 decades. 1 megahertz to 10 megahertz, 10 megahertz to 100, 2 decades increase in frequency. It's plus 20 decibels per decade, so if we have, it's only 0 that's dominating here, plus 20, so we will have plus 40 decibels. So approximately I can say this will be plus 40 decibels. So now we were able to plot a transfer function and also mark the steady state values, the infinite frequency and low frequency values, and also show the location of poles and zeros in the frequency response graph. In the same way, given a graph, we should be able to predict poles and zeros, and we should be able to write a transfer function. Now this is the transfer function that is given to us. From this transfer function, we should say what are the poles present in the system and what are the zeros present in the system. So start from omega equal to 0. As you keep moving here, you first encounter a frequency after which the gain starts reducing at the slope of minus 20 decibels per decade. So instantly you know omega 1 is a pole. So it's decreasing. So the transfer function will be something of this form, 1 plus s by omega 1. So there is one pole here. Now it's decreasing, and the moment it encounters omega 2, you see here the transfer function is becoming constant, which means the pole is trying to decrease it. If omega 2 was trying to increase it, then it will remain constant. So which means omega 2, if it was increasing it means it's a 0. So omega 2 here is a 0. So I can write 1 plus s by omega 2. Now after some time, when you keep traversing towards higher frequencies, at omega equal to omega 3, again the gain starts increasing with a slope of plus 20 decibels per decade. At that point, it means that you have encountered another 0. So omega 3 is also a 0. So it will be 1 plus s by omega 3. And finally, when you reach omega 4, again the transfer function remains constant, which means a pole and zeros effect is getting cancelled out. So omega 4 must be a pole. So it will be 1 plus s by omega 4. Had omega 4 not been there, the function would have just increased indefinitely. But because of omega 4, this is constant now, because omega 4 being a pole, it's trying to reduce it. So when you add the two effects, it's constant. So the pole and zero effect is cancelled out. So this is the transfer function. And the only thing missing here is the DC gain. DC gain here is given as 0 decibels. So generally we multiply this with the DC gain h of 0. So we get, again I'll talk more about DC gains and transfer functions in the next class. But right now you can take the DC gain is 1. So this is your transfer function for the system. I'll stop at this point. We'll discuss in greater detail in the next lecture.